In this thesis, we consider anomaly detection in autonomous driving multimodal signal sequences through deep learning and Bayesian models. First of all, what is anomaly detection? Anomaly detection is the process of recognizing that an observation or an experience is different from one's experience in the past. Now, for example, here we have a pedestrian area where pedestrians are walking, which is normal, and in the second case, we have a car which moves in the pedestrian area, which is not normal. Anomaly detection has a variety of applications across video surveillance, medical image analysis, traffic accident detection, and so on. And also, why is anomaly detection so important for self-aware evolving systems? Well, if we are given some training data, we can learn some models in it, and then we could be presented with some new data. We can perform anomaly detection on the new data, detect which data part is abnormal, and we can use it to perform the creation of a new model, allowing thus the system to evolve. And how do we perform anomaly detection? So in this thesis, we combine two different backgrounds, which are dynamic Bayesian networks and state estimation, and a deep neural network. First, we can go a bit into detail about dynamic Bayesian networks. So DBNs allow to model the relationships among random variables across time, and they can be used to represent and track the evolution of the state of an object. So if we are given some sensor observation X, we can obtain a state representation of it, Z. In this way, we have two models, an observation model that tells us how Z is correlated to X, and a prediction model which tells us how Z will change across time. We can use DBNs to perform anomaly detection by comparing what we predict with what we observe. Additionally, we can also add some layers to the DBN. In this case, the layer S represents a semantic category, and so each S represents 1 out of n modalities of change of the state Z. Also, in this case, we can compare predictions with messages that we get from the observations to perform anomaly detection. In this work, we use a Markov jump particle filter. Additionally, we use variational autoencoders, which are neural networks composed by an encoder and a decoder, allowing to represent images in a latent space in a probabilistic way. So each encoding is associated with a certain uncertainty value. Another problem must be solved when dealing with evolving systems is the continual learning phase. Artificial neural networks suffer from catastrophic forgetting. So if they are trained on new tasks and experiences, they forget how to solve the previous ones. So if we teach a neural network a task A, the performance of task A will increase. But then if we teach it a task B, performance of task B will increase, but performance of task A will decrease. Therefore, what we do is that we use the abnormal frames to train a new variational autoencoder, and this variational autoencoder can be used in parallel and then combined together in a single Markov jump particle filter during testing. To test our method, we used a dataset from a real vehicle called iCab. A human drives the iCab inside a closed environment, and different tasks are performed. Here we consider a perimonitor task for training and a pedestrian avoidance task for testing. Here we can see the different anomalies that are detected during the pedestrian avoidance, where a pedestrian is avoided during perimeter monitoring. So we can see different levels, an anomaly at content or frame level, an anomaly in the optical flow, so in the motion of the vehicle, and anomalies in green in the sequence of observations. Additionally, we see in the upper part the real image at time k, the predicted image, and where we are positioned in the map, and the zones color-coded that are assigned by the algorithm. Then we perform the continual phase. So after we detect the pedestrian anomalies, we train a new model, a model AP, that is able to recognize this situation, and we combine it with a previous model, model PM. So if we consider different situations, like a straight motion, a curving motion, and a pedestrian avoidance case, we can see how the reconstruction with one variational autoencoder is and how it is with the other variational autoencoder, and the prediction with the different models. So a model that only knows how to perform perimeter monitoring, one that only knows how to avoid the pedestrian, and a model that combines the two situations. And if we compare with the actual next image at the next time instant, we can see that the model that combines the two situations is the one that has a better performance. So in this thesis, we've combined dynamic Bayesian networks with neural networks with a probabilistic approach to detect anomalies and to perform continual learning. The references to the proposed method are in the slide. Thank you for your attention.